Today we're going to be talking about something called vectors. And a vector, the definition of it is a quantity with both magnitude, length, and direction. And we use those in real life for velocity, momentum, and force. So the vectors here that we have drawn, they're all equivalent because they have the same length or magnitude and they're pointing in the same direction. So it doesn't matter that they're in different locations. All we care about with for vectors to be equivalent is if they have the same magnitude or length and the same direction. So we notate a vector with a bolded letter and a line over it. And I know it's going to be hard for us or impossible for us to draw a bolded letter, so that's why we draw the arrow above it as well to notate that it is a vector v. Now, the arrow on top of the vector always goes in that direction. Regardless of the vectors going up, down, left, or right, it's always pointing to the right when we write it out. So vectors have a initial point, which I call the tail, and a terminal point that I call the tip, because it's pointed and it's the end of the vector. Now, if we label these points P, Q, we could also call this vector PQ. So just like in geometry, how there are different ways to name lines and rays, there are different ways to name vectors. And if you think about it, a vector is basically what a ray was in geometry. A ray had a starting point and it was going forever in one direction. And that's what these vectors look like too. So like I was saying, two directed line segments or vectors are equivalent if they have the same magnitude and direction. The three above there are all the same. To prove that two vectors are equivalent, you need to make sure that the lengths are equal and the slopes are equal. Well, for lengths to be equal, we use the distance formula. And for slopes equal, we use the slope formula. Now, a vector in standard position means that its initial point is the origin 0, 0. And from that, we can get component form of a vector. It's in standard position, and the coordinates of the end point or that terminal point are represented in that vector. So, for example, if we had something drawn here, and we have a vector at 0, 0, or starting at 0, 0, and going in this direction, and we called that vector v. This point right here would be your ordered pair of that terminal side. So v1 comma v2, or whatever numbers those are. But the component form of a vector uses these coordinates, but in a different notation. We use these symbols to notate that it is a vector. That tells us that this vector is starting at the origin and goes to or through that point. And we don't want to use parentheses there because parentheses just tell us that there's a point there, not that the vector starts at the origin and then goes in that direction. And then this you can also think of this as the horizontal component, comma, the vertical component of your vector. Because if you look over here, we make this a right triangle. This would be our horizontal component, and that would be our vertical component. Just like X and Y, we use that for our horizontal and vertical movement. Same idea for vectors. So now what if the vector wasn't in standard position? So if a vector wasn't in standard position, we're going to have to do some subtraction. So again, we're going to just pretend, and actually I'm just going to do quadrant 1 to make it easier for us to see. So here's 0, 0. But let's say instead we had our vector like that, with that arrow pointing this way. Okay, so to find the horizontal component, you would subtract your x values of these 2 points. And then our vertical component, we would subtract the 2 y coordinates of our 2 points, and that would give us the component form of a vector. And we're going to write that down here like in a type of formula, where if I have 2 points, P1 comma P2 and Q equals Q1 comma Q2, the horizontal components, so the vector would equal the x values subtracted, and it's always the terminal minus initial. So it's got to be Q1 minus P1. And I'm putting parentheses not because they belong in the problem, but because to emphasize you have to do that subtraction first. And then Q2 minus P2. Okay, and that would get you your component form of your vector. Your horizontal component, and then your vertical component. Now the magnitude or length of our vector, we use this symbol to notate magnitude, so like 2 absolute value bars. And we use the distance formula. Well, the distance formula, you have your x2 minus x1 squared and all that stuff. But if you have your vector in component form, you've already done the subtraction parts right here. So in component form, it would just be your horizontal component squared plus your vertical component squared. Okay, so once you get that into your component form of the vector, getting the like I said, the magnitude or the distance is pretty easy. So now let's look at example 1. Find the component form and magnitude of our vector with the initial point at -3, -5 and the terminal point at 5, 1. So remember, it's always the terminal minus the initial. So our vector is equal to 5 minus -3, comma 1 minus -5. Because, like I said, it's your terminal minus your initial. So then this is going to give us, this is going to give us 8, 6 as our vector. So our vector, if we had it starting at the origin, our horizontal component would be 8 and our vertical component would be 6. So now our magnitude is equal to the square root of our horizontal component squared plus our vertical component squared, which is equal to the square root of 100, which is equal to 10. So we found our component form. This is our component form right here. And we found our magnitude right there. All right, now example 2, we have the initial point at 2 comma -5 and the terminal point at -1 comma -9. So for our component form is going to be -1 minus 2 comma -9 minus -5. -1 minus 2 is -3, and -9 minus -5 is -4. So that's our component form, -3 comma -4, and then our magnitude, our magnitude is going to be the square root of -3 squared plus -4 squared, which is going to be the square root of 9 plus 16, which is 25. So that will give us a magnitude of 5. So yeah, finding your magnitude in component form is really easy. It uses the distance formula, but I would rather you do the component form first, and that makes the next the magnitude easier. Now we're going to talk about vector operations, adding, subtracting, and scalar multiplication. So if we multiply the vector by a value, we're not multiplying two vectors together, we're multiplying the vector by a value, a k value. A k value is being multiplied, and what you can think about it is that the k gets distributed to both components of our vector. So like if our k value was 3, we would multiply each component, the vertical and horizontal one, by 3. And it would go in the same direction. Unless you are having a negative k value, it changes the direction of the vector. So if we look at this drawing here, okay, if our vector is that right there, well, 1/2 v would be the same direction, but it would be half the length. 2 times v would be, the same direction, but then the vector would be twice as long. If I had negative v, okay, multiplying the vector by -1, it's going in the opposite direction now. Notice where the tip is. It's going in the other direction now. And then -3 over 2v. Okay, negative means goes in the opposite direction, and then multiply the coordinates by -3 over 2. So it's like dilations in geometry, where you just multiply the coordinate by the value by your scale factor. But now that we're doing vectors, we have direction to worry about. So if a negative k value changes the direction that we're going. So adding vectors, what we do is we position them so that the initial point, the tail of the second vector, is lined up with the terminal point of the tip of the first vector. So I call it tip to tail, like the tip of the first vector touches the tail of the second one. That sum is called the resultant vector. So for example, you see here we have two vectors, u plus v, and the order matters now that we're adding vectors. U plus v means I'm going to start with u, right here, and then I'm taking my vector v, this one here, and moving it so it starts there but it goes in the same direction. So my resultant vector is the start of the first one, vector u, goes all the way to the tip or the terminal point for the second vector. And you can see if we did the addition in a different order, I'd be taking this vector and starting there, and then my resultant would be, and this is probably not exactly where it would be, but you get the idea that, the order that we add the vectors makes a difference. So that makes graphing a little bit difficult. You just got to pay attention to the order. To add vectors algebraically, it is much easier. You add the two horizontal components together, and then you add the two vertical components together, and then you have your resultant. So a lot of times if you have a choice between adding it geometrically or algebraically is easier. But we're going to do both for these problems. We're going to find each resultant vector algebraically and geometrically. So let v be 3, comma, -2, and u be -1, comma, 3. Find u plus v. So u plus v is going to be, u is the x-coordinate and the horizontal component of u is -1 plus 3, the horizontal component of the second vector plus, comma, 3 minus 2. That's the horizontal component. So then my resultant is going to be 2, comma, 1. So now to graph this, we're going to start with u. U is -1, comma, 3, so 1 to the left and 3 up. So this is going to be my vector u. So I'm going to label that. And then my v vector is 3, comma, -2. So from this point, I'm going to go 3 to the right, 1, 2, 3, and down 2, 1, 2. So that it would be vector v. And let's just move this out of the way. So my resultant vector is this right here. This would be my u plus v. And you see how that corresponds with the algebraic one. We got 2, comma, 1 algebraically. Well, from the origin, if we go 2 to the right and up 1, we are at the end of that vector. So now letter B, u minus v. Okay, so we're going to start out with u, which is -1, comma, 3, and we got to subtract v. So -1 minus 3, comma, what was u again? So 3 minus -2. So that's going to be -4, comma, positive 5. Now to draw it graphically, again, we start with u, and u is -1, comma, 3. So 1, 2, 3. This is u. Then minus v. So v is 3, comma, -2, but we got to go in the opposite direction. So it's going to be -3 and up 2. So it's going to be in this direction. And then my resultant connects the start of u to the end of v. So this is u minus v. And you can see how it matches up again with our algebra. -4, comma, 5, left 4, 1, 2, 3, 4, and up 5, 1, 2, 3, 4, 5. So I just always do that to double check. Even if I'm not asked to do it algebraically, it is a good extra verification for this. All right, now letter C, -2v minus u. Well, instead of being able to go back and forth, I'm going to recopy the vectors down. So negative 2v will be negative 2 times vector v, which is 3 comma negative 2, minus we got u, which is negative 1 comma 3. So distribute, we have negative 6 comma positive 4 plus 1 comma negative 3. So up here, I did subtracting the vectors, and you can do it that way. In this letter C, I'm going to show you distributing the negatives so that your vectors are positive instead, so it makes it an addition problem. Because by doing that, you don't have to worry about, oh, I have to go backwards now. We can always make it an addition problem. Right, so algebraically, we're going to have negative 6 plus 1, which is negative 5. And then 4 plus negative 3 is positive 1. So we know where we should end. So now I'm going to add this vector. So negative 6 comma 4. 2, 3, 4, 5, 6. Then up 4, 1, 2, 3, 4. So this is vector negative 2v. And then I have to add this vector 1 comma negative 3. So from there, I'm going to go 1 to the right, and then down 3, 1, 2, 3. Oh, it's right where I wrote that. Let me move that now. So it's going to go this direction. That is negative u. And then our resultant vector goes from the start here. That is negative 2v minus u. And again, negative 5 comma 1, that point lines up with it. All right, I'm going to let you try letter D. And once you're done, unpause the video and see if we get the same answer. All right, so look at your answer and look at mine, and you can see the work that I did to get my answer. And hopefully this wasn't too bad. It's, again, you got to pay attention to the order that you are adding in, and that will give you the correct drawing. And unfortunately, if you do it algebraically only and you add them, well, then the order doesn't matter because it's just you don't look at the path. Like, you're still going to end up in the same spot, but your path is going to be a little bit different. Okay? So thanks for watching the video. Make sure to like and subscribe.